Okay, so let's talk about the following theorem. Let's read it. Let G star and the G prime dot be groups, and let phi from G into G prime be a group homomorphism. Then the kernel of phi with operation star is a normal subgroup of G star. Now remember that if you want to prove this, we want to show that for any element of a G in oper G, the left coset of the kernel generated by lower G equals the right coset of the kernel generated by G. But there is a criterion which is simpler. So proof. Let's show that if you pick an element of G, a generic element of group G, and a generic element of the kernel, that, let's write it. Let the lower G belong in upper G and H belong in the kernel of phi. Let's show that. Let's show that G star H star the G inverse is in the kernel. This criterion will make this proof very, very simple. What criterion are we talking about? Whenever this expression belongs to this subgroup, that subgroup is normal. Okay, so what does it mean to be in the kernel? It means that when you apply the map phi to the element, you get the identity of the target group. Now here I have recall that phi is a homomorphism from G into G prime. Okay, so if I apply phi to an element and I get the identity of G prime, then that element belongs to the kernel. So let me show that. Let's take this. I picked my element G star H star G inverse. I want to show that this is the identity of G prime. Okay, let's first use the fact that phi is a homomorphism. That is I can split this up as a G of, f of phi of G, phi of G dot from G prime, phi of H dot phi of G inverse. Recall that H does happen to be in the kernel, so this becomes the identity of G prime. So phi of H is simply the identity of G prime. So what happens when you take an element of G prime and you multiply it with the identity element? You just get that element back. So if you did this from left to right, phi of G times E prime is just phi of G dot phi of G prime, of G inverse, excuse me. If I've been saying G prime, I'm supposed to be saying G inverse. So there might be a correction to be made. Okay, this phi is a group homomorphism, so I can put this back in as phi of a G star G inverse. This is the identity of the G, so you get phi of E, the identity of G. We know that in a group homomorphism, phi of the identity is simply the identity of the target. Okay, so now we have verified that the expression G star H star G inverse, so phi evaluated at that expression, is the identity of the target. Consequently, by definition, that expression belongs to the kernel. So, consequently, G star H star G inverse is in the kernel. Okay, so that's the theorem. Okay, so let's do an example. The following example is an illustration of a major result of group isomorphisms involving the quotient groups. So example, let's recall the structure Z6 under addition modulo 6. C6, remember, is simply the set consisting of all remainders when you divide by 6. So 0, 1, 2, 3, 4, 5. And the addition modulo 6 is defined by the Cayley table. So plus is addition modulo 6, which is best identified using this Cayley table here. So plus 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, 0 plus 3 is 3, 0 plus 4 is 4, 0 plus 5 is 5. 1 plus 0 is 1 plus 0 is 1. 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, 1 plus 4 is 5, and then 1 plus 5 in the integers is 6, but when you look at addition modulo 6 is 0, because 0 is the remainder when you divide 6 by 6. 2 plus 0 is 2, 2 plus 1 is 3, 2 plus 2 is 4, 2 plus 3 is 5, 2 plus 4 is 6. When you reduce it modulo 6, you get 0. 2 plus 5 is 7, but when you reduce it modulo 6 is 1, etc. So it's in 3, 4, 5, 0, 1, 2, 4, 5, 0, 1, 2, 3, and then 5, 0, 1, 2, 3, 4. Okay, so that's how you define this addition modulo 6. So let's define the following function from Z into Z6. Phi of x equals r, where r is the remainder when dividing x by 6. So now I know what my structure's Z6 is. Now I want to use it in an example. So here's the example. Define phi from Z into Z6 by phi of x equals r, where r is the remainder when dividing x by 6. Okay, so first let's say observe the following. When you look at the group z with the addition of integers, and the group z6 with addition modulo 6. This phi right here will be a group homomorphism. So here, let me change ink because this blue is running thin. Hopefully this is better. So here, yes, it's better. So here, phi is a group homomorphism from C into Z6. So proving that requires that you show that when you pick x, y, and z, phi of x plus y is the same as phi of x plus phi of y, where the plus there will be addition modulo 6. So it is a little bit technical to do that proof. If you study number theory, you know that that is actually the case, that when you take two integers x and y and you add them, the remainder of that result when dividing by 6 is exactly the remainder of x plus the remainder of y when divided by 6 reduced modulo 6. So if you have studied number theory, you know that's a fact in number theory. If you haven't studied number theory, then you would have to go to the argument that we use in number theory to prove that fact. So let me outline that proof right now, assuming that we don't have a number theory background. So let's remember that phi of x is simply the remainder when you take x and divide it by 6. So here's what I'm going to do. So let x, y be integers. Now, I want to express x in terms of the remainder when dividing x by 6. So there is a way of doing that. X equals 6q1 plus r1, where q1 is some integer and r1 is in z6. And same thing with y. I can write y 6q2 plus r2, where q2 is in z, r2 is in z6. Now I have to do one more thing. I also have to look at the remainder of r1 of these two guys. So let so I'm saying let x be that, y be that, and then r1 plus r2 equal to 6q plus r. Now q here, there's only two possible values for q. Probably that's not so crucial, but there are only two possible values for q. That's a remainder when divided by 6. That's a remainder when divided by 6. So when you add them, you could still get a remainder when divided by 6, or you could get a remainder plus 6. Those are the only two possibilities. So here I'll say that q is either 0 or 1. And r is in r6. Excuse me, r belongs in z6, excuse me. Okay, so now let's do a direct calculation. Let's compute phi of x plus y. What is phi of x plus y? Well, let's do this a substitution. X gets replaced by 6q1 plus r1. Y gets replaced by 6q2 plus r2, but each of these are integer values, so we know that the group of integers under addition is abelian. It's associative. It has a lot of properties. So I want to use those properties. I want to commute these two elements because integers are commutative under addition. So I want to put 6q1 plus 6q2 plus r1 plus r2. But then let's make the substitution. What is r1 plus r2? Is 6q plus r. So you have 6q1 plus 6q2. The r1 plus r2 became that right there, 6q plus r. But then, what is phi of this number, or of this expression? Well, it better be r, because remember, phi of an element in Z is the remainder when you divide that element by 6. If you were to divide this by 6, the remainder would be r. Okay. So that takes care of the calculation of phi of x plus y. Now let's take care of the other calculation. Phi of x plus phi of y. What is phi of x plus phi of y? Now we know that x is 6q1 plus r1, and r1 is a remainder. We know that y is 6q2 plus r2, where r2 is a remainder. So phi of x becomes r1, and phi of y becomes r2. But now this is addition here plus in 6 plus. So when you add these two in that group, you get r. Because remember that this was just 6q plus r. This is 0 or 1. The remainder will be r. Okay, so conclusion. Phi of x plus y equals r, which is the same thing as phi of x plus phi of y. Therefore, we have established that phi is a group homomorphism from Z into Z6. So phi of x plus y equals phi of x plus phi of y. So phi from from Z into Z6 is a group homomorphism. Okay, so that verification is complete. Now, so let's now obtain two things. The kernel of this group homomorphism, and let's also compute the left cosets of that kernel. So now let's obtain one kernel of phi, two the quotient Z or kernel phi. And remember that these are just the left cosets of kernel phi. Okay, kernel phi, remember, so let's do that. Let's do the solving right here, right away. The kernel of phi, remember, is all elements in Z. So all x belong to Z, such that phi of x is the identity of the target. Now, here was phi. Well, the target is Z6. So what's the identity of Z6? It's just 0 in the Cayley table for Z6. When you think about integers whose remainder upon division by 6 is 0, then you're thinking of all multiples of 6. So that set is just simply 6z, or multiples of 6. Okay, so 1 is done. Now, here, now that we know that kernel of phi is 6, then in computing the left cosets of kernel of phi, we're just computing all left cosets of C6. And then all you have to say is, okay, so what do you get? You get a 6 itself, 6z itself, and then 1 plus 6z, which by the way is just the same as 6z plus 1, because this subgroup is normal. And then 2 plus 6z, 3 plus 6z, 4 plus 6z, 5 plus 6z. Okay, so there it is. Done with that. Okay, so let's now make a couple of remarks here. In this example, we have achieved the following. We have achieved from defining this particular homomorphism, which takes the group C into this other group C6, we've shown that it is a normal, that the kernel, we know that the kernel of that is a normal subgroup of Z, and we have that the left cosets, which are equal to the right cosets, is this set, this 6 elements set. Now, if I were to define my group, my quotient group, which is defined here, I will have to say, okay, so what is addition of a left cosets, which in this case are also is addition of right cosets. So let's define in addition. Define a plus addition in this quotient by the left coset x plus kernel phi plus the left coset generated by y of kernel phi. So these are two typical elements in z by 6z. So our definition is add x and y in z and then find the left coset of the kernel generated by that result. Okay, so that's my definition of addition of elements in this quotients, z by 6, 6. Now, it can be shown that, so observe that the structure z by 6z together with this addition as defined, boldface is a group. That's it. That's a typical exercise. So, but not only that, it is also isomorphic to the image of phi. So also observe that z over 6z with that addition is isomorphic to z6 under addition modulo 6. Now, if you wanted to verify what this is the case, you have to, of course, come up with an isomorphism between those two. Let me see if I can write it on the screen right now. So I cannot call it phi because phi is a homomorphism between Z and Z6. So now I want to find an isomorphism between this quotient group and Z6, which incidentally Z6 is simply the image of phi of Z. We'll write that in a minute. So here you have, if I can find it, I've written it previously. Well, let's do it this way. So phi, let's define. So here the isomorphism with isomorphism F. This time we'll do it in this direction. Go from Z6 into Z by 6Z given by F of X equals X plus 6Z. So this will be the isomorphism. It will be a homomorphism, or it's multiplicative or additive, excuse me. It preserves addition, excuse me. So here f of x plus y in Z6, when you apply f to x plus y in Z6, you get x plus x6 plus y plus z6. So that will show that this f preserves the operation. But it is also onto, because every time I pick an element, let's show that it is, let's see why it would have to be an onto map. So if I pick any left coset, so f from C6 into Z by 6Z is onto, because if I pick x plus 6Z in the quotient Z over 6Z, I can always reduce x to be between 0 and 6. So there exists for some x belongs to Z6. So I just say f of x equals this by definition. So you could say, what about if you put something like 11 here? Well, 11 plus 6z is the same as 5 plus 6z, and then you would use the 5 here. Now, for it being 1 to 1, so set, so f is also 1 to 1, so set fx equal to f of y, so that means x plus 6z equals to y plus 6z. What you need to show is that this x and this y are the generator, are essentially the same generator. So if you think of what does it mean to be 1 to 1, in this case, show me that x equals y up to a up to congruence modulo 6. And that happens. If this is 11, it reduces to 5. If this is 11, it reduces to anything that's 5 times 6k. Okay. So in this latter remark, that Z 6Z under addition of left cosets is isomorphic to C6 addition modulo 6. If we realize that C6 is actually the image of phi, so C6 is the image of Z under phi, and 6z is simply the kernel of that same phi, then we can rewrite our isomorphism here as Z over kernel of phi under that operation equals to the image of Z under phi. Okay. And this is addition modulo 6. And that's supposed to be isomorphic. Okay, so in this transcription here from this notation into that involving the isomorphism, the homomorphism phi, we are leading to the following idea that if you have a group G, so this holds for not just Z and C6, this holds for generic groups and normals in the kernel, which is normal subgroup. So let me see, I'll get it here from my notes so I don't slaughter it. Nope, don't have it in the notes, at least not right here. So this suggests a more generic result. So this suggests the following. So you have a group homomorphism. So phi from a group into the image. Whatever the image is, you have to be some other group. So G into phi of G, where G is a group and phi of G, the image, under some other operation, call it dot, is a group. Then the quotient G by the kernel of phi under star is isomorphic to this guy here. So then the quotient G to kernel of phi together with star together with a star. I have to define the star. I'm going to make this one boldface star is isomorphic to the image of G under phi with whatever the operation is there. Here the star is how we're going to define a binary operation between cosets. So so x star kernel phi, so where x star kernel phi upper star bold face star y star kernel phi is defined to be x star y in G left coset generated by that. which of course will be the same as the right coset because the kernel is a normal subgroup. Okay, so we'll leave this video at that. That's all. Thank you.